Hey everyone, welcome to today's lecture. Super excited to have you here. Before we jump into things, I just want to tell you a little bit about ATAR Notes. We are dedicated to supporting students like you with heaps of free stuff, like today's lecture, as well as premium resources. And on our website, we also have thousands of free notes, videos, articles, and stuff you can access. And we also have study guides that you could purchase through our online store. Also, I just wanted to tell you about ATAR Notes Plus. ATAR Notes Plus is our new online platform where you can access all of our study guides, where we have heaps of neat trial exams and more online stuff for a super affordable price. But yeah, so that's all the stuff that we have to offer on the site. So yeah, without further ado, we'll get into today's lecture. So today's lecture is QCE Physics 3 and 4. So this is part of our January lecture series, and my name is Taya. I don't know if I've said that yet, but my name is Taya. But yeah, it wasn't that long ago that I also went through physics under the QCE system. I graduated in 2022, so not last year, but the year before. So I know the stress that you're going through, and I know all kinds of tips and tricks that should help you. But yes, if you have any questions or queries or concerns, feel free to pop them into the live chat and they will be answered throughout the live lecture. So let's get started. So just a little bit about me. So once again, I graduated in 2022 from St. Augustine's College, so that's somewhere over in Ipswich. I'm currently studying engineering and commerce at the University of Queensland. And once again, if you have any questions to do with the content that we're going to cover, my degree, what uni life is like, feel free to ask in the chat. But yeah, today is about physics, so primarily if you have any questions related to the stuff we cover, that's what will be prioritized in the chat. So welcome to grade 12, and we are here at ATAR Notes and Shootswide to help you out. So yeah, have a good time during this lecture. Hopefully you'll enjoy it. And yeah, let's just get started. So today we're going to cover the topics in red. So we've got gravity and motion. That's for topic 1 of unit 3. So we're going to cover vectors, projectile motion, inclined planes, circular motion, gravitational force and fields, and orbits. You may have started some of these already, probably the first 3, but if you haven't, don't stress, because we're going to cover the basics of it and how we can apply what we learn to questions. And then we're going to have a little look at electromagnetism, specifically electrostatics, and the topics under that will be explored when you go back to school. But yeah, anyway, let's get started. So this lecture is aiming to give you a snapshot of some of the Unit 3 topics and tips leading up to your final year. So today is a perfect opportunity to take knowledge from someone who has been through exactly what you're about to undertake. Like I am able to provide you guys with a lot of study skills, what things to remember when you're going through these questions, what do you need to include, what don't you need to include. There will be some things that I will emphasize highly, so please take note as we go through. But yeah, I'm going to give you an overview of not only the content, but also the necessary skills that you'll need leading up to those externals. I know your pain, so hopefully the skills I will share will help you out with that. So let's just get started with the content. So vectors. So vectors are projectile motion. Vectors are dealt with a lot throughout the entire year, so please do not neglect them. They are something you have to remember, because they do end up being worth quite a few marks on the external. So a vector is a quantity defined by a direction and a magnitude. So for instance, say a boat was going east at 10 kilometers an hour. That has not only direction, but it also has magnitude, the direction being east and the magnitude being 10 kilometers an hour. If you were to just say it's going east, then that's not a vector, that's a scalar quantity. So you've got to make sure it has both of those. It's often useful to split up vectors into horizontal and vertical components, and we will have a look at this a bit more when we get into projectile motion. So for instance, to calculate vertical height or horizontal range of a projectile. So as we can see here in the little picture, projectile motion consists of separate horizontal and vertical velocity vectors. These vectors are independent and occurs simultaneously. Simultaneously means at the same time, if you're not so sure. Gravity would only accelerate the vertical component of the motion, whereas horizontal velocity would be constant, assuming that there is no resistance. That is really important to remember, and I will underline that. Assuming no resistance. But assuming is the key word I'm talking about here. Reason being is because when you go through a lot of physics questions, it doesn't necessarily just have to be vectors of projectile motion. You have to remember your assumptions. And it's good to listen, that way you know what variables you do need or don't need. Because what do they say? Oh, air resistance does count or doesn't count. You've got to remember what's important to you answering this question. So they're saying assuming no resistance. This could mean air resistance. So that basically means that either Vx, or in this case maybe Ux, is constant between these parts, because they each have the even number of spaces. They're all the same size, so that means the velocity in the x direction does not change. However, due to gravity, Uy, or Vy, depending on how you look at it, I'm just going to call it Uy, the strength of gravity, that acceleration due to gravity, brings that cannonball closer and closer to the ground faster and faster. So it starts off really weak and then it gets stronger. So you could see that these gaps tend to widen. But yeah, always remember that Ux, or the horizontal component of velocity relatively stays the same, assuming no resistance, whereas vertical velocity changes due to gravity. Alright, now let's get into the formulas that we need. So we've got a few here that we're going to deal with, and I've already kind of talked about a little bit about some of these variables, but we're going to go over what each of them are, because sometimes people see S and they're like, wait, what is that again? Wait, why is it SY? Wait, why is it squared? So I'll go over what each of these formulas are for really quickly. But before I even do that, I just want to say, in physics, at least for the QCE system, gravity is 9.8. It's not 9.81, it's not 9.79, as I've seen in some textbooks, it's 9.8. Just leave it as 9.8. But yeah, so just remember that it's always 9.8, and that's what it says outright in your formula sheet as well, so just stick to that. Okay, to the formulas, so let's look at this first one. So we've got Vy, and Vy is velocity in the y direction, so the vertical direction. And I'm just going to do a little drawing down here. So say something gets thrown up in the air and comes down to land. As you saw on the last slide, I used Ux and Uy, and there's a reason for that. So I'll show you now. Up until about this point, initial and vertical velocity is signaled by u. So this is initial velocity in the horizontal direction. This is initial velocity in the vertical direction. Oh wait, did I say horizontal for the bottom? Horizontal is ux, uy is vertical. There you go. Sorry if that was confusing, but it's the u stands for like initial velocity. Okay, and then if I get another color, you'll notice throughout this lecture that I love using the different colored markers. Yeah, because then the ball in this scenario reaches a point where velocity in the y direction reaches 0, and then it just starts descending, all in the while when ux or vx stays the same. So now it starts turning the other way after that halfway point. So this is Vy, so that vertical velocity changes its direction. And then we've got that horizontal velocity. Okay, so that's how it works. That's what each of these variables are. So you got ux being initial horizontal, you got uy being initial vertical velocity, you got vy being final velocity that's vertical, and then you got vx, which is final velocity in the horizontal direction. You get the gist. Anyway, it doesn't have to be a very specific name, but that's what that means. So back to this first formula. To calculate the final velocity in the vertical direction, it is equal to gravity times time plus the initial vertical velocity. Sy is vertical displacement, and then you know the rest of those variables. Yeah, and then one key thing here to remember that people always tend to forget when doing questions is that Vx is equal to Ux, okay, because that horizontal velocity never changes. And yeah, I'm pretty sure that's it for those. If you have any questions, pop them into the chat if you're not sure about any of these. But just so you know as well, say you've got a variable that you don't know in one, but you can utilize another formula to help you out. Like say you're trying to find Vy, but you don't know Sy, so you got two unknowns. You could always use this one. That was a bad scribble. You know what I mean? To plug it into there, provided you know what time is and what Uy is, but you have to know what Uy is anyway for this part. So you can really manipulate these formulas to work in favor of what you do or don't have. Alright, so let's get started on some questions. So we've got here an arrow is shot at 40 meters per second at an angle of 45 degrees above level ground. So we're going to do A on this page. Draw a diagram showing the trajectory and initial velocity vector. So, alright. So it gets shot straight up in the air like that. I'm just wondering. I'm going to say it just kind of goes down like that. I know it's really bad, but for this question, all we're really concerned about is it meeting like this point before it starts descending. Yeah, because down here we start talking about maximum height. Actually, I might just redraw that because I'm not too happy with that little drawing. Might just clear the whole page. Cool. Alright. So we're going to say it goes up like that. Alright. Yeah. So we've got 45 degrees. It was shot at. And the initial velocity, so just a u, because they're not giving us a vertical or a horizontal component, is 40 meters per second. Alright. And then this is kind of like the halfway point where it starts going the other way. So we've shown the trajectory. Just put in arrows just in case. And the initial velocity vector. So this is the initial velocity vector here. The one that I draw very poorly. Okay. Now we need to calculate the horizontal and vertical initial velocity of the arrow. So we'll probably do it on this page as well. Call it B. I don't know how to do all the letters. Sorry about that. Okay. So you might be thinking, okay, how on earth do we calculate uy and how on earth do we calculate ux? If you've already started this, then terrific. Put it in the chat and that will be checked. But yeah. So this is being fired, and uy is opposite this angle, okay? This is the hypotenuse, so think of it like trigonometry, SOHCAHTOA, and this is adjacent. So to calculate ux, that's our adjacent, so we're going to be using cos. So cos uh, 45 degrees multiplied, oh not multiplied, sorry, that was a mistake. Cos 45 is equal to ux divided by 40, because that's our hypotenuse. And now we multiply both sides by 40 to get ux by itself, and we are left with a number I need to plug into my calculator, but put it into the chat if you've calculated this. So cos 45, and also make sure if you're doing methods or specialist and you're using a graphics calculator, make sure it's in degrees, not radians. Yep, so you should have gotten an answer of 28.28. And that's in meters per second because we have to use the same units. Okay, and now it's going to be very similar for uy, but this time we're dealing with opposite and hypotenuse, so we're going to use sine. So sine 45 is equal to, what's her name, uy over 40. Then once again you multiply both sides and you will find that uy and ux is the same, 28.28, and that's just because that's the way the math works. we just happen to get both the same answer. And if you wanted to check this and like do some of the Pythagorean theorem, then by all means check, but you will end up with 40 if you were to do so. But yeah, so 28.28, that's ux, and it's also uy. Okay, now using that, we now need to calculate the time of flight of the arrow. So we're going to go over here, see the time of the flight of the arrow. So for this, we are going to need the formula Vy is equal to gt plus uy. Now, because we do not know what Vy is, we are going to say that it is 0, because initially Vy is nothing, all right? And we're just going to use the initial velocities that we have, but our final velocity we do not know. So Vy we don't know, Uy and Ux we do know, but we don't need Ux, we just need Uy. So we're going to put 0 is equal to 9.8 times t plus uy. Oh, and I just want to say as well, this is like an approximate value. I rounded that. So just make sure you get the curly equal signs. Plus uy, which is 28.28. Okay, and then we're going to rearrange, so this is going to be negative 28.28. Which is equal to 9.8 t. Now you're probably thinking, hey, we're going to get a negative answer. Well, remember that gravity is actually a negative value, so we're actually going to end up with a positive value. And even if you did end up as a negative value, just negate the negative and just treat it as a positive. But in this case, we know that gravity is normally negative. So negative 28.28 divided by negative 9.8, that's going to be 2.8, I'm going to round it to 2.9 seconds, 2.89 I should say. Always round to 2 decimal places if they don't specify what you need. Alright, next we need the maximum height of the arrow, so we're going to do it on this page as well. So the maximum height. This is where we need, where is it? Yeah, sorry, I was just looking at my little note there. So we've got v squared y is equal to 2g sy. Sy is what we're trying to find because they're saying horizontal range. Oh wait, no it's not. Is this the right formula then? Oh, sorry, I was looking at the very last one. I was meant to be looking at the one above it. Sorry if I just confused you guys. Calculate the maximum height. Yeah, then that's fine. Sy is fine because height is dealing with the y direction. So we need to find out what that will be. So the reason why we're using this formula, and I'll just say why in a second so I don't get muddled with my words as I write. At the maximum height, uy and vy is equal to 0 at this point. Reason being is because the velocity slows down so much to the point where it comes to a full stop in the air, and then it starts to descend. So uy and vy are equal, which is 0. Okay, so this is going to be 0, and this is going to be 0. So let's do, oh, actually, is that fine? Didn't write it in my note. I've just got down here in my note that only Vy is going to be 0. But the thing is, if both of them were to be 0, then you'd find that Sy is going to be 0 in the end, because you can't divide 0 by anything. That puts us in a bit of a pickle. Little bit of a pickle. Just quickly see if there's another way we can figure this out. I think we'll just make Vy 0, because that's what my note said, and I didn't write the justification for it. But I think, just thinking about it, I mean, logically, Uy would also be 0 at that spot. But it can't be, for the sake of math, so... I think we'll just use the Uy that we have, and then we'll just leave Vy as 0. I think that's what we'll do. Because then we've got 2 times 9.8, and if this is incorrect, then it will be put in the comments. Or you guys can figure it out and then share amongst yourselves. Multiplied by Sy, which is what we're trying to find, plus U squared Y. So that's going to be 28.28 squared. Alright. And then we're going to move this over here, because we need to get Sy by itself. So I'm just going to quickly calculate what that value is. That's going to be 799.75, but that's going to be a negative because we're moving it over. Oh, it's actually be 0.76. And then we've got 2 times 9.8 times Sy. Yep, and we're going to divide the other side by 2 times 9.8. So then we're going to end up with Sy is equal to a number, and that number will be okay, we're thinking here negative 40, but once again we can't have a negative distance. We're just going to negate the negative. I'm going to say 40.8. So apparently, according to our math, at 40.8 meters high, that displacement, that's when we reach our max height. Now let's do E. All we need for this one is displacement in the x direction is equal to the initial horizontal velocity multiplied by time. and hopefully you guys can read that. So that's just going to be equal to 28.28 multiplied by 2.89. So 2.89. Oh, it's literally right there. Yep, 28. Yeah, 0.28 times 2.89. And this will give us our horizontal displacement. Yeah. Yep. So our horizontal displacement will be 81.73 meters. If you have any questions about this question, feel free to pop them in the chat. Otherwise, we will move on now. All right, inclined planes. Hopefully you guys would have done a little bit of this already in last year's term. My school definitely did, and I know a few other schools do, but it really depends on where you go. But this is a good topic to really understand well, because it's worth a lot of marks. So, vectors, inclined planes. Obviously, mass, it's an amount of matter in a body, and it's measured in kilograms. Whereas we have weight as well, and that is the force of gravity which acts on a mass when placed within a gravitational field. And that is measured in newtons, and those are the units that we describe them in. And we also have a thing called normal force, and normal force is the contact force perpendicular to the surface of the object, and it's measured in newtons. But yeah, I think the best way to really learn this topic is to just kind of practice it, and that's what we're going to do at the moment. So first of all, we need to calculate... Oh wait, did I even read the question? I don't know. Maybe not. Question 2. So this diagram depicts a free body diagram of a 1,000 kilogram roller coaster on the first drop of the ride. It asks us to calculate the net force and acceleration of the roller coaster, and we have to assume a negligible effect of friction and air resistance. Once again, keyword here is assume. We don't have to worry about friction, and we don't have to worry about air resistance. So first things first, we are going to calculate the force due to gravity, so this bit here. And the way to calculate that is by writing F, force due to gravity, is equal to mass times gravity. And like I said earlier, the way to calculate that is our mass. So we got 1,000 kilograms multiplied by 9.8. All right, and then we will end up with 9,800 newtons. Okay, and our next step now is to calculate the parallel force. So that is the force going this way. And the way we write that is by going like this. And that is equal to the force due to gravity where is my note? Sine theta. Okay. Yeah, so this is the parallel force, sorry, I just realized. But parallel force here, that's actually also called net force. All right? And we're using this to calculate that. Because if you think about it, we're using the opposite. This is the opposite, and this is the hypotenuse. And we're forming a little like triangle here. And that's how we know we're going to use sine. All right, so we've got 9,800 multiplied by sine 60. And make sure your calculator once again is in degrees, otherwise you'll end up with a very wrong answer. By the way, this is the same thing as FNet. I just learned it a couple different ways at school. And then when I go around to external, I was like, wait, which way did QCEE want again? So 9,800 multiplied by sine 60. And that is 8,487. 0.05. Newtons. So that is our net force that we've just calculated. Whoop. And now we need to calculate the acceleration, and the way we do that is we go F is equal to mass times acceleration. So how fast that roller coaster is moving down that slope. So we've calculated the force at which it's moving down that slope, and now we just need that acceleration. So we'll plug in the numbers that we have, so 8,487.05. Oh, and once again, sorry, I rounded this. A lot of these are just rounded. 0.05 newtons. Is equal to 1,000 times acceleration. We divide both sides by 1,000. So now acceleration is equal to 8.49 approximately. Sorry, the approximate symbol. 8.49 meters per second, which is quite fast. Alright, if you have any questions about that, feel free to ask in the chat and they will be answered throughout the live stream. Alright. Now we've got this question. So it asks us, the diagram below shows an object initially at rest on a frictionless plane. Calculate the time it will take for the object to slide 10 meters along the slope, and we are to show all working. And just with the end bit there, show your working, make sure you show as many steps as possible, because a lot of half marks are awarded, even for just units, writing the empty formula, then filling in all the variables that you do or don't know, rather than just jumping straight to the answer or plugging in the numbers and then spitting out your answer. Sometimes showing those 3 or 4 steps actually does come a long way marks wise, so make sure you're including as many as possible. Yeah, so we need to calculate the time it'll take for that object to move 10 meters along the slope. So we need to use the formula force due to gravity to calculate mass, the mass that we're dealing with. So we know that the force due to gravity is 45 newtons, but we're going to use that knowledge to find out what our mass is. So we've got force due to gravity is equal to mass times gravity. Yep, so we've got 45. Is equal to mass times 9.8. Yep, so now we divide both sides by 9.8. And we end up with 4.59 for our mass. Kilograms, that is. Make sure you remember your units. They're worth half marks. So 4.59. So not a very heavy object. Cool. Rightio. What was I going to say? Now we need to calculate, our next step is to calculate the parallel force. So the force parallel to the object. And that is equal to, what was I going to say? Yeah, so I'm pretty sure that's like, that's it, like going down the slope here. Yeah, so that's going to be Fg multiplied by sine theta and that's going to be equal to 45 times sine 30. Right. And then we end up with 22.5 newtons for that. And now we need to calculate the net force. So F net is going to be equal to the parallel force multiplied by the frictional force that we get given, which is 12.5. So it's parallel minus FA or FF. It's friction. Well, it says frictionless, so it's going to be FA. So we've got 22.25. Not 25, sorry. 22.5 minus 12.5. And that's going to be equal to 10 newtons. Cool. And now we need to use what we calculated there to find the acceleration. So now we're going to use F is equal to ma to find the acceleration. Do we have the mass? Just trying to figure out where I got. Don't know where I found the mass from. I've got a mass and I'm like, where did it come from? Oh, we calculated that first. Sorry. Yeah, there it is. I was like, where did the mass come from? Okay. Yeah, carrying on. So we got mass times acceleration. Sorry about that. I was like, did we calculate the mass yet? That's going to be equal to 10 newtons, 4.59 multiplied by A. Divide both sides by 4.59, and your acceleration will be 2.81 meters per second squared. Yep. And now we need to use that to finally calculate our time. So it was a lot of steps to get to that point, but we need to find out what that net force is in order to find out what that acceleration of that object is overall. So now we're going to use a formula S, and sorry, I just realized I forgot one little letter. Yep, so that's going to be, where did it go? All right. Yep, SY. Yeah, so we're going to use this one. So SY is equal to half GT squared. I gotta remember this really quickly. Wait. Where did it go? Write mine different. Yeah, so we're actually going to modify this one a little bit. So I'm going to write down the original. So SY is equal to half GT squared. If my computer will let me. Yep, so SY is equal to half GT squared plus UYT. Oh, there we go. Yeah, so we're actually going to modify it a little. Where are we at? Okay. Yeah, so this is going to be half, and this is going to become acceleration, because we're dealing with down. Actually, I'm wondering if we have all the variables for this. We do, sorry. Oh, and it's not going to be S. Y. It's actually just going to be S because it's the acceleration going down. Which is why it's not going to be this top formula, which is why we're going to modify it. Yeah, so it's going to be half A... Oh, is this one in your formula sheet? No, I'm wondering. Okay, I've got this formula here. It should be in your formula sheet. It basically looks like that top one, but just a little different. So it's S. I'm pretty sure we used this one when I was in physics. UT plus half AT. But the only thing is that we don't have that. So, just thinking, what we're going to do is we're going to say 10 meters. Doesn't look quite right. I don't think it's going to end up right at all. Well, maybe. Radio. I think I'm just overthinking. It's like earlier when I couldn't find the mass, and then the mass was literally right there. We had already calculated it. Initially at rest. Oh, maybe that's the hint here. Okay, yeah, initially at rest. That means that U is going to be 0. Sorry about that. Brain had a moment. Yes, so it's going to be U times T, so it's going to be 0 times T plus half times the acceleration we calculated, which is 2.81. Multiplied by our time. Yep, so we're going to end up with 10. Is equal to half times 2.81 times time. But what we're going to do is we're going to actually go back a step. I'm going to make a little bit more room. And just have this already divided. So divided by half times 2.81. And that's going to be equal to time. It's now time. Sorry, just make sure this thing's going. Yeah, cool. Yeah, so 10 divided by half times 2.81. We end up with 7.12 seconds. That's how long it takes to travel, to slide 10 meters along the slope. Okay, if you have any questions about that, feel free to ask. They will be answered momentarily. Alright, we are now on to uniform circular motion. So, just thinking, because I think we might be going a little fast. Yeah. Well, how many questions do we have? 1, 2, 3, 4. Oh, we should be fine. Alright. Yeah, so I'll just explain what circular motion is. So we got uniform circular motion. It is an object traveling in a circular path with constant speed is said to be undergoing uniform circular motion, so such as the satellite orbiting the Earth. So as you can see here, say you've got like a stick with like a string that like goes out to the edge, and then you know, like when you're a kid and you got a ball on a string and you just like twirl it round and round and round like a helicopter. It's like this. So you've always got that equal force going in, and that velocity is always perpendicular to it going out in that one direction. Okay, so that is constant velocity just heading out in that direction. So now we need to define the concepts of average speed and a period. So velocity for circular motion is defined as 2 times pi by the radius divided by the period. And those are all measured in its respectable units. So velocity is measured in meters per second, and then you have the radius of a circular path. It's measured in meters, so that will be this distance here along the dotted line. And I'll just give you a little legend here. So this is our radius. Obviously you've got the velocity there, and then you've got the period to do one rotation. So it's like to go from here all the way around back to there. That was such a bad drawing, but you get the idea. To do one revolution, to do one rotation, it takes so many seconds. So the object's velocity at any point is directly tangent to the circle. Okay, so the magnitude equal to the distance covered in one complete revolution is divided by the time taken. All right, so the velocity will be higher if less time is taken, or if so it's like you have to have that ratio right between the radius and the time. So say you complete a radius in a very low amount of time, then that means you have a greater velocity. But say your radius may be bigger, but it's taking you just as much time. So say to go in a radius, to go in one revolution where the radius is like a meter, and it takes you 3 seconds to complete it, then, that's like our base, right? But say it takes you 6 seconds the next time round. That means your velocity has decreased because that ratio has then decreased. So the radius and the period here really work hand in hand. So it's just a matter of, make sure you got your units right when you calculate it as well. But you might get some questions where you might get a graph on the external and they might say, compare the radial distance with the period taken, and you might say, the greater the radius, the more time is taken, or the smaller the time is taken, the greater the velocity. But yeah, and you might do not the research investigation, but an experimental investigation, and you might use circular motion. You might measure the amount of time that it takes to do certain revolutions at different distances, and then you might graph that and compare. It's just an idea, but I saw some people do that. It is quite hard the more distances you do, but it's just to, prove those theories, that the greater the radius, the more time is taken, yada yada yada. It really depends on how you choose to write those predictions. Alright, now we're going to look into a couple more definitions here. So we've got centripetal acceleration and centripetal force. I'm just getting some water. Okay. Yep, so centripetal acceleration, it is calculated using that formula. Acceleration is equal to velocity squared over the radius. And that's the acceleration towards the center. So acceleration, once again, is measured in meters per second squared. whereas velocity is measured in meters per second, and then obviously the radius of the circle is measured in meters. Whereas you've got centripetal force, which is measured by Newton's second law, F equals ma. There must be a net force directed toward the center to cause this acceleration, which is called a centripetal force. So this centripetal force, the formula then becomes mass times velocity squared divided by the radius, the force of which is moving toward the center. So just like how we have here, this is that centripetal force. Yep, so that's measured in newtons. Once again, our velocity is the same, the radius of the circle is the same. So now we're going to do this question, and this covers the criteria that's above that. So solve problems involving average speed of objects undergoing uniform circular motion, and solve problems involving forces acting on objects in uniform circular motion. So it's really integral that you understand how to do these kinds of questions, because they are multiple step. Everything we're doing today, all these questions are multiple step questions. When you start getting into the more theoretical stuff that you'll find in Unit 4, like, what's it called? I forgot what the topic's called. Not quantum theory, although that's interesting in itself. Oh, what is it called? It's like the one where you've got like twin A goes off to outer space and then comes back. It's where you've got like the different perspectives. You know what I mean. You know what I mean. And if you don't, then you will see. You've got some topics where it's quite conceptual in the way where you've got to like answer it in sentences and stuff, whereas the content we're covering today is much more mathematical, and you have to remember lots of little things when doing these calculations, such as for inclined planes. What is net force? What is force due to gravity? Vectors, it involves magnitude and direction, or for circular motion, what the different forces are and where are they moving. Yeah, and there's a lot of different formulas to remember, but most of them, I should say, are in the formula sheet. But yeah, that's just something I just want to point out. But yeah, if you have any questions about that, feel free to ask. Without further ado, I think we'll just get started with these questions. So we've got about 1, 2, 3, 4 questions left for today. But I do want to say as well, if you feel confident in doing these questions, if these are topics you've already done before, by all means go ahead and do them and then check your answers as I go. But if you haven't done these before and you feel like you should have, or you're just worried about them, don't stress, because it is still very much early days. You've got months and months until you have the exam, and this is stuff you may not even have covered in school yet, so I wouldn't stress too much. But yeah, just do what you can, and hopefully most of what I say makes sense. But once again, if you have any questions, feel free to ask. And if there's something you're not so sure about, but you want to go ask your teacher, take a photo, ask a friend, check your textbook, check the ATAR notes resources if you have access to them. But yeah, all the support you need is around you. So yeah, we'll just get into this question now. So a car with a mass of 1,000 kilograms travels around a roundabout radius of 10 meters at 60 kilometers an hour. So we've got our radius and we've got our velocity. Calculate the acceleration of the car while in the roundabout. So first things first, I just want to convert this into what we need, which is meters per second. So, so to put that into meters, we need to go 60 times 1,000, so it's going to be 60,000. So now we're in meters per hour, but we need meters per second. Yep, and there are 60 minutes in an hour, and there are 60 seconds in a minute. So it's going to be divided by 60 times 60. So divide by 60 times 60, so it's going to be 360. So now we're going to end up with this calculator. 1.66.67, I'm going to say. I feel like that's very fast. Is that too fast? Doesn't look like it. If there's anything wrong, or if you notice anything wrong, feel free to put it in the chat, because that would be good to know. I'm sure this wouldn't have been the first mistake I made, but I checked all this beforehand, so we'll see. I think we'll just go with that number, because if you think about it, there are 60 minutes in an hour, so you divide it by 60 to find it for 1 minute, and then you divide it by 60 again to find it for a second. So that looks fine. So we're just going to say that it travels at that. Alrighty. Yeah, so calculate the acceleration of the car while in the roundabout. So we have converted all that. So now let's put down A. So we're going to use the formula acceleration is equal to velocity squared over radius squared. So now I'm going to put that number 1.66. Oh wait, no, sorry, 166. Ooh, sorry, I'll just erase that. The reason why as well we converted that to meters per second is because that's how we talk about velocity in physics, but also because our radius is in meters, so everything has to be relative. Divided by radius squared. Yeah, so 10 squared, so that's just going to be 100. Yep. So that's going to be, put in the calculator. That's going to be 277.79. Meters per second squared. Now for B, I'll use a different color. They say to calculate the net force on the car. So for this, we're going to use F is equal to MA, or F net, I should say. Alright. So we're going to say it's 100, oh, not 100, sorry, 1,000 multiplied by 277.79. Yep. And that's going to be a very big number. That's going to be 2,770, oh wait, no, it's a very long number. It's going to be 277,788. .89. And this is an approximate, by the way, because I rounded. Once again, that's going to be in newtons. So a lot of force. Yeah, and there shouldn't be any errors there because it looks like all the units are right. But if you spot any errors, feel free to sing them out because it would be good practice for you. Now we're going to go on to C. So calculate the time the car takes to go around the roundabout. So put C over here. Now we're going to calculate time. So we're going to use the formula V is equal to 2 pi R over T. And that's another reason why we converted our velocity to meters per second as well, because our period is measured in seconds. So that was 166.67, so that's what we're going to put over here. It's equal to 2 pi. Oh, and our radius. Pretty sure it was 10 meters. Yep. And that's over time, or the period. So now we multiply both sides by the period, our unknown variable. But now we need to divide both sides by 166.67 to get the period by itself. So now it's going to end up being 2 pi times 10 divided by 166.67. Cool. Now I'll put that into the calculator. I'm just thinking, for this part, put your calculator into radians because we're dealing with pi, yeah. So 2 times 2 pi times 10 over 166.67. That is going to be 0.37, and that does not look right. What happened there? If I put in degrees, does it change anything? Probably not. No. Okay, apparently it takes no time at all, and it's 0.37 seconds. Or 0.38 once we round. Something's happened there. Something meant to be squared, actually. Apparently it's full text. The only reason why I would see an error would be in our conversion in the beginning. But everything seemed okay after that. Yeah, because if you think about it, 60 goes to 60,000 because you have to multiply 60 by 1,000 to get from kilometers to meters. And then to go from hours to minutes, you divide by 60, but then you divide it by 60 again. So unless that's something that happened there, that would be it. Oh, would you look at that? Okay, yeah, don't do what I did and divide by 360. Divide by 60 and then divide by 60 again, because otherwise you'll get the completely wrong answer. I was actually meant to go one more decimal place over. Sorry to be annoying. Learn from me, learn from that mistake. I was like, these numbers are a little big. Just a tad big. By about a 10th factor. Yeah, so it's actually going to be like that, which makes so much more sense. So now I'm just going to go through and quickly change everything. So sorry if you've written it all down in pen. Hopefully you used pencil or a pacer. But yeah, we'll just fix that up now. And I'm going to do it in a different color, which I am currently, so that you can see the change. Sorry for the confusion. You're all probably in the chat going, finally, she noticed. After all that doubt. But hey, I'm human. Everyone makes mistakes. Good thing I picked up on it eventually. So that's actually going to be 2.77, but it's actually going to be 2.78 by the time we round. Meters per second squared. I'll change the thing over here. And that answer's going to change down here as well. Yep, so it's going to be 2.71. I mean, 78. Okay. Yep, so that's going to be 277, and I also just kept that number earlier from in my calculator. So it's going to be 2778.89. That's our force. Now here, where we went wrong, well, I went wrong, not we, I, is here. So hopefully we should end up with a much larger distance, not distance, time. And also, if your numbers ever look funky, always backtrack. So always do what I did and just backtrack and just double check because, well, you saw what happened. It could save you a lot of marks. It could really just be a little savior in itself and just, you know, might be the difference between getting that A or B. So I'll just get rid of that. So what was it again? It was 1 point, wait, why? Oh, it is, sorry. 16.67, yep, okay. And this was not squared. Don't know why, I just did a little dot there. Ignored the dot. 16.67. Alright, hopefully that's a bit of a better answer. So, back in radians, not that it really makes a difference. Or at least for this question, for some reason. Times 10 divided by 16.67, and hopefully we get a better answer. There we go. Takes 3.74 seconds, and that looks a lot better than 0.38. Alright. Now we're up to D. What would happen to the force required if the car speed doubles? If friction between the tire and the road is unable to provide this much force, what will happen to the car? Okay, we'll deal with the first part of that question first. And we're going to do it right next to B because it's talking about the force. So I'll get green. And we'll redo it here and see what happens to the force. So F net is equal to mass times acceleration. I'm just realizing the car speed doubles. Okay, so say this is the speed, right? So this actually needs to double. Oh, okay, so we actually have to do a couple things. Sorry, I'm going to backtrack again. We're going to calculate acceleration again and then force again with that new speed, that doubled speed. And we're going to do it in green. So D, and that formula was A is equal to V squared over R squared. Yep, so it's going to be in brackets 16.67 multiplied by 2 squared over the radius squared, which is just 10 times 10, which is just going to be 100. And that should give us, oh, no, I don't know what happened there. Alright, that gives us, I just put the wrong number in, hold on. That's better. Alright, that gives us 11.12 meters per second squared, yeah. and we can compare that to the last one. So it's significantly like a higher rate than the previous acceleration when velocity gets doubled. Now let's see what happens to the force. So the force it's a mass, so mass times acceleration. And our mass will be, what's the name? 1,000? Wait, is it 1,000? Yeah, 1,000. Multiplied by that acceleration, which is 11.12. And we get 11,120. Newtons. And let's compare it to the old one. We had 2,778.89, whereas we've got that here. So we could always do a bit of a ratio of that just to see how it changed. So we could always put, seeing as velocity 2 is now greater, we could always just do like v2 over, sorry, I put that little 2 in the wrong spot. I'm not actually trying to square it, I'm just trying to do a little ratio comparison. v1 over v2. So we can always get the first answer and put it over the other one. Yeah, because we need to answer that first question in like a word answer. So we could show that ratio and say, well, according to the mathematics that we've used, it, you know, triples or something like that, which is why we're doing this little ratio. You could always do v2 over v1 or v1 over v2. We could do both and just see which one we prefer to say. So that v1 is going to be 2778.89. Yep, and then we're going to put 11,000 at the bottom. I'll just see what we end up with. Alright, we're looking at 0.25, so it's like a 25%, it's like a quarter. So v1 is like a quarter of v2. So it's like we're looking at 1 over 4. So I think just based off that, it'd probably be nicer to show v2 on top of v1, just so we can say, hey, it's like 4 times the size. So 11120 over 2778.89, 78.89. Yep. Yeah. So we could say like a word answer, and I'm wondering if I can actually type. I can't. But what we can use, just by doing a little ratio comparison like that, we could say the force required as the car speed double. When the car speed doubles, the force required by the car multiplies by 4, goes up by 4. It goes up by a factor of 4. But yeah. Now to answer the second question, if friction between the tyre and the road is unable to provide this much force, what will happen to the car? Well, this is essentially just about the concept of speeding. If you go too fast on a road that can't handle that much force, that much acceleration, the car will go out of control and just spin and eventually crash. Which is why on roads we have speed limits, because those roads can only handle so much. That's why when you go over a speed bump, you can only go about 20k an hour, because if you go any faster, you'll end up being a bit of a flying car for a few seconds, and then you'll cause some serious damage to your car. That's why these speed limits are important, and that's what this question is getting us to understand. If we provide too much force in a place where the speed is too slow for that secondary speed, then the car won't be able to handle it and it'll crash. Okay. Alright. How are we going? Alright. We've got 3 questions left. So we've got Newton's law of gravitation. So we're now up to gravitational force and field. This is a very large-ish topic. I don't know, actually. I feel like vectors, projectile motion, and inclined planes, they're all kind of grouped in together as one topic. Whereas gravitational force and fields and orbits are kind of grouped together as well. And electrostatics kind of ties into the second topic of Unit 3. So, yeah, anyway, back on topic. But first, I'm going to have some water, because it is a hot day. Alright. So, Newton's law of universal gravitation, and I advise you guys to memorize this if you can, because what QCEA tend to do when they write the exams, especially for physics and chemistry, they like to say, pick the right definition for Newton's law of universal gravitation, or the definition of a vector, or something like that. And the wording might be slightly off. And if you actually look at the syllabus, sometimes they actually provide exact definitions that they want you to remember. So that's why those syllabuses are really important as well. So make sure you're making flashcards or palm cards with these definitions. So the law is every object with mass attracts every other object with mass in the universe with a force called gravity. So, and that is where we use the formula. Force is equal to the universal gravitational constant, which is provided to you in the formula sheet, multiplied by the two masses. So mass 1 and mass 2 are the two objects you're dealing with in the space, divided by the distance between the center of mass squared, and that's measured in meters. So now we're going to get started on this question. So this covers the criteria to solve problems involving the magnitude of gravitational force between two masses. In the past exams I've seen, they tend to have at least one of these in part 2 of the exam. So make sure you know this content pretty well. Alright. I think personally, and I'm just gonna say this, I might be totally different to other people. I found Unit 3 harder than Unit 4 because Unit 4 was a lot of theoretical, whereas Unit 3 is a bit more mathematical. So I found that Unit 3 needed a bit more practice, which is probably why they teach it to you first. So just keep that in mind. I just wanted to say that before I forgot. Calculate the gravitational force the sun exerts on the Earth, given that the radius of the sun is 6.95 by 10 to the 5 kilometers, and its mass is 1.496 by 10 to the 8 kilograms. The radius of the Earth is 6380 kilometers, and the distance between them is 1 astronomical unit. Now, I just want to make a note here. 1 astronomical unit. I have never seen when I was studying physics at least, I have never seen them use the term astronomical unit. I looked at the formula sheet, couldn't find it for the life of me, so I don't know whether this is something that is now needed to be memorized. Because that's actually something I had to go and Google, an astronomical unit. It's essentially just like 1 light year, I found out. But yeah, anyway, I'll share that with you in a minute. But if you wanted to start putting it into that formula and have a go at it, I advise you drinking a bit more water, which is why I say to get started now. But remember your conversions, because these are given to you in kilometers, and you need your distances between the centers of mass to be in meters. And that's something that always trips people up. Alright. So I'm just going to get started. So we've got force. Is equal to that constant, multiply the first mass by the second mass, big M and little m to distinguish between the both, divided by radius squared. So now we've got our constant, which is equal to 6.67 by 10 to the negative 11. And the computer is going to die. Well, at least it showed me the notification. Had plenty of charge. Had. Keyword had. Yeah, so by 10 to the negative 11. Multiplied by that first mass, which is going to be 1.496 by 10 to the 8. Multiplied by 5.97. Let's make sure we're using the right one too. Yeah, 5.97 by 10 to the 24. Okay. Now, all that's going to be divided by, it's going to be a long division symbol, our radial distance. And we also need to convert this into meters as well, all of this. So first we're going to put it in one big bracket, like that. And then we're going to do another little bracket. I'm going to start writing it in, so 6.95 by 10 to the 5. plus, because we've got to add these radial distances, 6380. Yeah, so those first two, those are the ones that they give us. The radial distance of the sun, and the radius of the Earth. And now we've got the astronomical unit, which is 1.5 by 10 to the 8. So plus 1.5 by 10 to the 8. By 10 to the 3. And that 10 to the 3 is to go from kilometers to meters. And this is something that a lot of people forget. And then you square all of that. And yes, that is a lot of numbers in one spot. It is a little daunting, but it will be okay, I promise. Now, we chuck that into the calculator, so bear with me while I do that. So 6.67 multiplied by 10 to the negative 11. Brackets are very important in physics. I need to emphasize that as well. The number of mistakes that get made because people don't use brackets is insane. Very important. Okay, I'm up to the denominator now. Alright, we've got a number. The force is, and I feel like this is really low now that I look at it. It is a positive number, but I'm just thinking I might just put in a couple more brackets just to be safe. When in doubt, add more brackets until your calculator says no. No, same answer. Okay. 2 point, and hopefully you got the same answer too. 2.62 newtons. That was it. Oh, that's rounded, by the way. So, wavy lines. And yeah. So that's what I ended up with. That is the force. That is the gravitational force that the sun exerts, and I'm pretty sure that is quite low. I'm wondering why. Because it has to be in meters. So it has to be multiplied by 10 to the 3. It could... No, I don't see a mathematical error there, so we're just going to go by that answer. If you have any questions, or you're not so sure, or you all ended up with a completely different answer to me, then please put it into the chat. I'm just looking back and forth here. I feel like that should all be... I feel like I should have ended up with a much bigger answer. Oh well, that's okay. Alright, gravitational force and fields again. So a gravitational field is a mathematical description of the region of space about a massive body, for instance a planet, in which other masses feel a gravitational force. So at any point P in space, as a force of gravity felt per unit mass placed at that point. And this is where we have that formula. Gravity is equal to the force of gravity divided by mass towards the planet's center or down. This formula isn't really used a lot. It's literally just a variation of what we've been using earlier, which is the force due to gravity is equal to the mass times gravity. But yeah. These are probably used a little bit more. So we've already talked about that top one, but it's literally, yeah, it's what we've done already with the formula we just looked at, but instead we've just replaced force with gravity. That's it. But we've also included, I don't know why they've involved D at the bottom if we're not actually using D. They're literally just been about R. This is R. Not to confuse you. This gets provided, once again. Yeah, so this is the gravitational field of the planet, okay? Alright, orbits. So these I advise you to memorize, because, like I said earlier, like the multiple choice questions that they give you, they tend to be like, recall the second law, or which laws support this, or that, or etc. Or this is happening to this planet. According to Kepler's third law, describe what is happening to the radius. Like, they kind of tend to vary, but the Kepler's laws always seem to somehow get involved in exams, and you probably have seen this when looking at them. If not yet, then you will. So yeah, so make sure you remember these. Kepler's first law, it's all orbiting planets orbit in an elliptical fashion. So in this shape here, okay? So it's not an oval, it's like more an elliptical shape. Kepler's second law, it's a line joining an orbit body to the center of its orbit, and it will sweep out an equal area in equal time, okay? You don't really do much with the second law in terms of calculations, it's more so third law here. So the third law is the ratio of the cube of the orbital radius to the square of the orbital period as a constant for a given body being orbited. I'm pretty sure that's given to us here. So the empirical relationship between the period and the radius of an orbiting satellite and the mass of a central body being orbited. That's all to do with the third law. So we could see that here. So we've got the radius cubed divided by time squared, the period of the orbit squared, is equal to the gravitational constant multiplied by the mass of the central body being orbited divided by 4 pi squared. This formula does tend to come up quite a bit, so and it is quite confusing to most. So practice this one religiously, because you'll have to compare like the radiuses and the times between planets and stuff. You'll have to prove that third law. So let's get crack-a-lacking on this question. So it says, the Earth takes 1 year to orbit the Sun at a distance of 1 astronomical unit. And if they talk about astronomical units in the exams, they should provide it. That's how it should be. You shouldn't have to memorize it. From the surface, calculate the mass of the Sun. The radius of the Earth is 6,380 kilometers, and the radius of the Sun is 6.95 by 10 to the 5 kilometers. And do we have space on the next page? We do. Okay, so we're going to use a formula that we just looked at. So radius cubed is equal to time squared, or the period squared, which is equal to the gravitational constant multiplied by the mass divided by 4 pi squared. Alright, and we're going to remember that the radius is going to be in meters. So, we need to make sure we add all three of these. So this bit, that bit, and this bit. Alright, so just thinking, yeah. So it's very similar to what we did in the previous question. And we're just going to make sure we multiply it by 10 to the power of 3 to get it from kilometers into meters, because there are 1,000 kilometers in there are 1,000 meters, sorry, in a kilometer. So we'll write that in. So I'll just start with the first one. 1.5 by 10 to the 8. And remembering that we are trying to find the mass. Plus 6380. Plus 6.95 by 10 to the 5. Multiply by 10 to the 3. More brackets. Squared. Over period, which is 1 year. Wait, but isn't that in... It's in seconds. Oh, would you look at that? So now we're going to do some magic math here. So if you think about it, 1 year, we've got 1 day, which is 24 hours. So we've got 24 hours, but then it's got 60 minutes in each of those hours, which has got 60 seconds in each of those minutes. And then you've got 365 days a year. So it's going to be a long number. It's going to be 36,000. Squared. Oh, I just realized that one's actually cubed. We've got the gravitational constant, which is G. Multiply that mass. Divided by 4 pi squared. What I might do, just because we're running on a little low on time, I might just quickly zip through this question and just put it into the calculator and tell you what the answer is. So we got 1.5, 10 to the 8, plus 6380, plus 6.95 by 10 to the 5, by 10 to the 3. 315, 6, oh wait, 36,000, squared. Divided by 4 pi squared. Oh, it's not divided by, it's multiplied by. Sorry. And then we're dividing by the gravitational constant, which is going to be 6.67 by 10 to the 11, negative 11, I should say, sorry. And that's going to be, our mass is going to be very big. It's going to be 2.04 by 10 to the 30 kilograms. Okay. We're going to go on to the next question. Okay. But yeah, that formula can be rearranged. This is something worth remembering, that it can be derived by the relationship between Newton's law of universal gravitation and uniform circular motion. So yeah, just keep that one in mind. Yep, so onto electrostatics. This is a very important formula to know. This one will be provided to you, and Coulomb's constant will be provided as well. You have to remember that point charges will be attractive if the charges have opposite signs, and repulsive if the charges have the same sign. I'll let you pause and take notes there, but I'm going to move on. That is the charge of an electron. Says to calculate the magnitude of electric force between two electrons placed 1 millimeter apart. And I'm just thinking, did I even... Wait. I think we're going to move on from this question because we don't have a lot of time. But we'll do... I think it was this question instead. Yeah. Alright, to calculate this one, calculate the electric field strength at 2 centimeters from a charge of 2.5 coulombs. So we got the work from A to B is equal to the electric point charge of A minus the electric point charge of B. Is this the question that we're going on? Oh, sorry. Where did it go? Oh, this is the question that I prepped for. Okay, so I just missed 2 questions completely. Alrighty. Well, I'll just give a quick rundown of how these questions are meant to be done. Ignore that for now. Quite literally, just make sure you have the charge of an electron. Because you'll need it for Q here and Q here, because those are the charges. For the 2 electrons, they give you the constant, and the radial distance is 1 millimeter. So just make sure for the radius here, you convert it into meters. That's all there is for that one. Yeah, so ignore that math there. Make sure that you put in 2 centimeters here, but make sure it's in meters. And this is 2.5 coulombs. This is the formula that you'll be using, because you're only talking about 1 point charge. So this is where you have that information from here. And then this is a bit of a challenge question. So I should have started with this one. There's only a little bit of working, but I'll just talk through it really quickly. Long story short, you need the negative of your work, so you're going to end up with -5 by 10 to the -5. And then you need that value, and you need to divide it by the charge that they give you, and then that should give you your answer. Sorry, I don't have time to write it out. But yeah, so to solve A, it's just the negative of your work. To solve B, you have to take that negative of the work and divide it by that charge that you're given. Alright, so today we looked at gravity and motion, and a little bit of electrostatics. So just a motion, just a moment. Yeah. And just some tips on how to remember stuff. So to learn this kind of content, we've got a few different options. This is some of the stuff I've found particularly helpful. I highlighted flashcards here because I use them religiously when going on a bus, before and after class. And yeah, just whenever I shouldn't have been on my phone and I was like, okay, I can make better use of my time, I always pulled out some flashcards. They do take some time to make if you're making them your own. Otherwise, you can find some ones that are pre-made online. And you can just print them, or you even got websites that are just dedicated to physics. So another thing you can do is draw out the system. So draw out your diagrams, draw out your projectile motion, inclined planes, and label. Do mind maps, Cornell note-taking, active recall, what's the most important info and how can you use it to your advantage. Make sure you talk about those formulas, those units. Work with a friend as well that might be studying at the same time. I found that so helpful because, you're all going through it together and you might as well, help each other out. And this one, last one I don't do personally, but a recorded recall. That's totally up to you if you want to use that one. I never used it personally because I couldn't watch myself back, but if that's your boat, then yeah, you do it. Anyway, those are some general study tips. You can have a look at it on the download. Those are some general exam tips. And yeah, hopefully you guys enjoyed today's lecture. If you have any questions, pop them into the chat. We'll still answer them. Otherwise, we'll see you all next time. Have a great day.